Let's talk about Chapter 8, Comparative-Static Analysis of General Function Models. So in the previous chapters, we talked about the partial differentials. So for a partial differentials, let's look at this equation here. So suppose we have m variables, right, from x1 to xn. And partial differential means we just focus on, for example, x1. We just focus on the change of y given the change of x1, right? And we assume that all the other variables stay the same, right? So all the other variables stay the same, and what's the change of y because of the change of x? So this is called partial differentials. But here in Chapter 8, we'll focus on a new term called total differentials. So again, we have a function. It's called the function z. And z is a function of x and y. So z has two variables, x and y. Both x and y can affect the value of z. So just similar to this case we learned in Chapter 7. So the total change in z is approximately the change caused by changing x plus the change caused by changing y. So as I said, for partial differentials, we only focus on the partial change of y because of only one variable, right? And all the other variables stay the same. But this is only partial, right? We just look at the partial effect of changing only one variable. But for total differentials, it's called total differentials because we want to find out the total change if all the variables change by a little bit. What's the change of z? Or what's the change of y, the dependent variable? Right, so for example, so in this example here, z is a function of x and y. If y doesn't change and x increases or decreases a little bit, the change of z is called partial derivative or partial differential of x with respect to z with respect to x. But what if in the other case both x and y increase a little bit, right? Both x and y increase just a little bit. So x starts from x0 and it becomes x0 plus delta x, and y is from y0 to y0 plus delta y, right? Both x and y just increase a little bit. So now the change of z is called a total change in z. Because the change in z in the second case is from two sources. Both is from two sources. The first source is the increase of x, and the second one is the increase of y. Right? So this is called the total change of z. And the total differentials is the change of z when all the variables change a little bit. Right? All of them increase a little bit or decrease a little bit. That change of z is called total differentials. So look at the definition here. Let z is a function of x and y, and it's continuous. So it's continuous, so it means that it has differentials in all the values or all the ranges of x and y. So you can take the differentiate of z anywhere in the range, right? It's continuous. So let dx dy represent changes in x and y. So we use fx and fy to represent the partial derivatives with respect to x and with respect to y, respectively. So the total differential of z is this equation. So dz equals to fx times dx plus fy times dy. So this is just a partial z over partial x and the dx plus partial z over partial y dy. So the total change or total differential, we call that, of z is the summation of two things. The first one is the partial derivative of x times dx. So this part is the change of z from the change of x. So as I said, the partial derivative means the rate of change, right? So partial z over partial x means given this small change of x and all the other variables stay the same, the change of z. So this term is called partial derivative, right? This is the definition of partial derivative. So if this thing times dx, this means that the first part means the change of z given this change of x. And you times the change of x, right? Dx means the change of x. So these two things is cancelled, right? Or just think of that should be cancelled. So this becomes something like this, right? Or the change of z. So to put it another way, so partial, this sign, is kind of similar to delta z over delta x. But this means the partial sign means the change of z with respect to change of x, but all the other variables stay the same, right? So it means the rate of change. And if you times a small change of x, it becomes the absolute change of z, right? It becomes this thing. So the first part here equals to the change of z given the change of x. And the second part here, partial z over partial y, then times dy. It means the change of z because of the change of y, right? So we add them together. So this becomes the total change of z equals to the change of z because of the change of x plus the change of z because of the change of y. So we add the two parts together to get a total differential or total change of z. Right, so this is the equation of how to calculate the total differentials. And if z is a function of n variables, not only two variables like y and x and y. So in general, if z is a function of n variables from x1 to xn, like this, so we can also write a total differential function, but this will be a little bit longer because you have n variables. So you have to add each of them one by one, right? So dz equals to partial z over partial x1. So this is the rate of change or partial derivative of z with respect to x1. Then times the change of x1. So this term becomes the change of z given the change of x1. And this is the change of z given the change of x2. And then so for the last term, this is the change of z given the change of xn. And you add all the terms together to get a total change of z when all the variables change a little bit. Right, so dz is called a total differential or total change of z. Okay, so let's see three examples here. Find the total differential for the following functions. And we assume that a, b are positive numbers. So first, f x1, x2 equals to a x1 plus b x2. So we have, like, for all the three functions, there are only two variables. So I can use the function here, right, to solve that. So the total differential of the function should be the partial derivative times dx and dy. So here we first find the total differential, we first find the partial derivative of the function to all the variables. Right, so here is partial f over x1, and this is a. And then partial f over partial x2, so this is b. Right, so we first find the partial derivative of the function to all the variables. And then we use the function here to find out the total differential. So f1, the f1 means the partial derivative of the function f with respect to x1. Right, and then this is a partial f over partial x2. So this is a, right? Just a plug in here, dx1 plus b times dx2. So this is the change of df, right? So the change of df, the interpretation is just the change of df comes from two ways, right? So the first is the change of x1. So dx1 means the change of x1, right? But the change is very, very little. So we use d, now delta, to represent that. So the first is a change of x1 times a, and then plus the change of x2 times b. So when x1 changes or increases, this one increases, and a and b are both positive, so df should also increases, right? So this is like interpretation of df, and what's the meaning using to represent df using this equation, right? So the change of df is a function of a change of dx1 and a change of dx2. So for the second case, the function is x1 squared plus x2 cubed plus x1, x2. So again, there are two variables in the function, and we first need to find out the partial differentials of the function f to all the variables in the function. So the first is partial f over partial x1, and the second is a partial f over partial x2. So take the partial derivative of x1, so this becomes 2x1 plus x2, right? So 2x1 plus x2. We just consider x2 as a constant when we take the partial derivative of x1. And for the second, it should be 3x2 squared plus x1, right? So in this case, we take the partial derivative with respect to x2. So that means that we take x1 as a constant, and we take the derivative. So the total change of f equals to f1 times dx1 plus x2, f2 times dx2. So this is to plug in the partial derivative, and then times dx1, and then plus the second partial derivative times dx2, right? So this is a partial derivative. So I can see from this function, the df, the total differentials of df, is still a function of x1 and x2, right? In the first example, a and b are constants. So there's no x1 and x2 in a function. But for the second case, df is also a function, is also related to the absolute value of x1 and x2. So if you want to find out the partial, if you want to find out the total differentials of x1 and x2, you need to plug in the values of the specific x1 and x2 to find out the total differentials. Okay. So for the third one, so the function is x1 to the a times x2 to the b. So first, partial derivative of f with respect to x1. So this should be a times x1 to the a minus 1, and then times x2 to the b, right? Because this is considered as a constant, so we just copy the value here. So for the second one, it should be b times it should be b times x2, b minus 1, and then times x1 to the a, right? Because x1 to the a is considered as a constant in this example. So we just take the derivative of x2 to the b to find this thing, right? And then we plug in the total differentials and to find the function like this. So this is how we find out the total differentials. Just use the equation here and here. Okay. And then we have some of the rules of differentials. So for these rules, you may be familiar with that because we've talked about that, the similar ones in the previous chapters. But let's review that again, right? So let k be a constant, and u and v be two functions of the variables x1 and x2. So we have the following 5 rules. The first one is a constant function rule. So dk will be just equal to 0, right? Because k is a constant. So the differentials of any constant is just 0, because the rate of change of a constant function is always 0, right? So the total differentials will still be 0, right? Because the value doesn't change. So this is number 1. And then the rule 2, the derivative of c times u to the n, c is a constant, right? C is a constant here, just equals to cn times u to the n minus 1 times du. Right. So if we take the derivative of this function, it's just cm times u to the n minus 1, which is the power function rule. We talked about that before. The times the small change of u, du. Right. And then the third one is called sum difference rule. The derivative or differential of the u plus or minus v just equals to the summation or subtraction of du and dv. And so we can get rid of the parentheses by applying the sum difference rule. So for the fourth one, it's a product rule. The differential of u times v equals to v times du plus u times dv. Right. So this is just similar to the derivative rules. We've talked about that before. Right. But the derivatives, we don't they're slightly different, but it's really similar to that, right? So for the rule 5, it's called quotient rule. So the differential of u over v is just a v squared, 1 over v squared times v du minus u dv, right? Okay. So here are some of the 2 examples. So we have a function like this. So y is a function of 2 variables, x1 and x2. And we want to find out the differential of y, right? So we want to find out dy. So the first way we find the dy is to apply the total differential function like this, right? We first find out the partial y over partial x1, and then find out the partial y over partial x2, and then times dx1 and times dx2 respectively, and then add them together. Right, so this is a formula we have talked about that here. But because we have learned the rules of differentials, so we can just apply these rules of differentials to make the calculation easily, right? So for example, so dy we don't have to calculate the partial y, partial x1 or something like that. We can just write, because we have the total differential rule here, right? So we can write dy as d 3x1 squared plus x1, x2 squared, right? And so we have the rule 3. So rule 3 tells us that the summation, the total differential or the differential of the summation of two functions is just the differentials of the first one plus the differential of the second one, right? So this is just a d 3x1 squared, the first one, and then plus d x1, x2 squared, right? So this is rule 3. And then we get this, we're here, and then we can apply the rule 2 for the first one, right? The power function one. So this becomes 6, or we can write this as 3 times 2x1, 2 minus 1, right? This is a power function rule. And then dx1. So this is just a 6x1 dx1. And for the second one here, we can use the rule 4, which is a product rule, right? So we can think of, because we have two variables here, right? It's hard to just take the derivative if you have two variables. So we have to use the product rule, right? So these are two variables. For each variable, we can think of that as an independent function, right? So here in this example, we have dx1, x2 squared, right? But we have two variables. We cannot just apply to the rules. We cannot just calculate the differentials easily. So we let u to be x1, v to be x2 squared. So we have two functions here. And then we'll apply the product rule. So duv equals to v du plus u dv, right? So d x1, x2 squared equals to x2 squared, right? This is v. Du, u is x1, and the plus u, which is x1, times dv, right? dv is just dx2 squared. So we get this function here. And then we apply another power function rule to the second one here. So this becomes x1 times 2x2 to the 2 minus 1, and then dx2. Right, so this is just 2x1 x2 dx2. So we get the final result here. So this is a 6x1 plus x2 squared times dx1. Right, we just combine the similar terms together, the common terms together. And then the second one here becomes 2x1 x2 times dx2. So this is the final result of the total differential of y. So for the other example here, we have this function, and so we want to find out total differentials of y, and we can use the rule 5, right, the quotient rule. And so we can create two sub-functions, right? So u equals to x1 plus x2. The v equals to 2x1 squared, right? So by the quotient rule, so dy should be equal to 1 over v squared times v du minus u dv, right? That thing. So v is this function, 2x1 squared. So the square of v should be 4x1 to the 4th, right? And then times v du. So this is v, this is du, right? And then minus u dv. And then we can apply the power function rule to here, and then the sum difference rule, right? So this becomes, again, 2x1 squared times, this is the sum difference rule, times dx1 plus dx2, and then minus, again, this is u, and then we'll apply the power function rule, so this becomes 4 times x1 times dx1, right? And then we can combine the compound terms together, combine dx1 terms together and dx2 together to find out the result, which is this one, right? Okay. So for the examples here and for the rule here, we only consider two functions, u and v, and both of them are functions of the two variables, x1 and x2. But we can also have an extension, like here. We have another two rules. So first is that we have three functions, and each of them are the function of x1, x2, or other variables, right? So the differentials of u plus or minus v plus or minus w, we have three functions here, is just du plus minus dv plus minus dw, right? So we can get rid of the parentheses by taking differentials of one by one and add them or subtract from them together. Right. And for the product rule, again, d u times v times w, the product of the three functions. And the differential of that is just a v times w times du, and then the other two times dv, and then the other two times dw. So we calculate du, dv, dw, and we use the other two functions. We use the product of the other two functions and times the du, dv, or dw respectively, and then add them together to find out the total differentials, right? Which is similar by the extension of the product rule here. Okay.